uh, basically we try to see जो हमारा ये two particle state which was there, how we could see two particle state in continuous one particle state and quantum field theory operators. And we took both जो इसके continuous eigenvalues as well as discrete eigenvalues. How we could have a representation of them. So in the meantime, we also incorporated Bose-Einstein statistics and Fermi-Dirac, जो इनकी symmetrization and anti-symmetrization जो condition है, the algebra. And at the end, how we could find is that जो हमारे पास psi of sigma, or sigma 1 or sigma 2, so on, or sigma n was basically, and we could represent it like that. Zero factorial. So psi, so this space sigma 1 or psi sigma 2 or 2, so on, psi sigma n or psi n. Yes. So we could represent it like this. So now the question is, for example, so with respect to permutations, जो subscript हमारे पास हैं, subscripts which we do from 1 to 2, so on and so forth, psi is symmetric in Bose-Einstein case, and psi is antisymmetric metric in Fermi-Dirac. So this much you know. And accordingly, the algebra जो इसका है, when it's Bose-Einstein or when it's Fermi-Dirac, it will just accordingly, the signs will get flipped in that sense. Side that, for example, in trivial case, जो हमारे पास है, for one particle, not for two particle, because in principle, जो Fock space है, it will be n1, n2, n3, so it may be n particle space or subspaces. So each subspace may be representing one particle states, two particle states, so on and so forth. So in trivial case, for one particle case, one particle state, n is equal to 1, psi of r sigma can be denoted as r sigma is denoted as 0 times psi of sigma, or so we can have for this, so we can only have psi sigma 1 can be this one particle state, and the last one is psi. So we can represent it like this. And in the meantime, we can say this can be represented as R sigma or represented by for one particle state. So we can also represent it like this. So which represents one particle Schrodinger wave function with spin representing psi. अब हमारे पास what we are going to say is for the thing is that whether we have one particle state, so whether we have Fermi-Dirac state or whether we have Bose-Einstein state. For n particle states, in 3n configuration जो हमारे पास है, 3n dimension Cartesian coordinates XYZ coordinates में, तो जो हमारे पास जो size है, size under exchange of that spin, you can see you can have symmetrization condition and anti-symmetrization conditions, which we did in the, so we saw while symmetrized or anti-symmetrized जो हमारे पास commutation relationship है, there is a sign change inside. Either we'll have a commutator or we'll have an anti-commutator in that sense. So fog representation जो हमारे पास है fog representation which is basically these places occupying the fog space uh, with an emphasis on with intrinsically indistinguishable one particle properties which जो हमारे पास हैं uh, they are constrained by these symmetric and antisymmetric relations. Otherwise, their occupation cannot be explained otherwise also. तो अब हमारे पास what we can say is like this. We can say now we can come prepare to this thing that if psi n psi n as a state can be represented at sigma 1 sigma 2 so integral of जो हमारे पास if we just give numbering to this first degree it's 56 if we just number it so जो हमारे पास state है for n particular state we can represent it for n1 factorial it's psi dagger sigma n or n फिर or n minus 1 or n minus 1 and so on and so forth psi sigma dagger or psi sigma dagger like last में और आएगा या हमारी get state है and the other state which is represented by psi or sigma 1 or sigma 2 so on or n sigma n. So in three-dimensional space it's d3 d3 or so on and d3 or n. अब हमारे पास है कि how can we just arrive at this lemma? So we want to basically incorporate जो हमारे पास continuous eigenstates हैं और discrete eigenstates हैं which we can have इसकी representation fog space. How we can have a representation then? Now these continuous and discrete states की eigenvalues they should have both these symmetrization condition and anti-symmetrization condition. उसको हम if how can we represent it in this sense so that's it so we have to invoke when we took those relations the third तीसरी वाली equation थी उसमें हमारे पास canonical delta use होता था we could have that thing. So we are going to use for a proof for Fn which is the lemma which is required is 0 of psi of sigma 1 r1 psi of sigma 2 r2 so on and so forth psi of sigma n rn psi of sigma n dagger rn psi of sigma n dagger rn prime and psi dagger sigma 1 r1 0. So it's equivalent to sigma n. So we can have permutation. Now we can see for these. So इसमें ये है कि जो कल हमारे पास equation थी last one. If you remember, for a particular psi sigma r prime psi sigma double r prime minus psi sigma double prime r double prime psi sigma prime ये एक computation थी तीन आ रही थी. The third one was like this. R prime psi sigma dagger R double prime minus psi sigma dagger R double prime psi sigma R double is equal to delta R minus R prime. You can see there is a canonical delta. So taking this thing since it wants to use symmetrization condition or anti-symmetrization conditions, so how can you invoke this delta R? So if R is equal to R prime or R is not equal to R prime. So for this, we can just write this equation. हमारे पास it will be like this: sigma 1 R1 psi sigma 2 R2 so on psi sigma Rn. तो ये अपना है psi sigma dagger Rn ये 1 और 2 आएगा 1 आएगा फिर psi sigma dagger 2 आएगा psi sigma dagger ये आएगा so on. But you could have this will be equal to permutation of sine of this plane R2 minus R1 इसी तरह R1 minus R2 prime इसी तरह delta R2 minus R2 prime इसी तरह delta Rn minus Rn prime अब we can represent them in terms of delta sigma 1 sigma 2 like this for one particle states yes sigma 1 sigma 1 prime delta sigma 2 sigma 2 prime delta sigma n sigma n prime so anybody has to ask anything so यहाँ तक है ना it's fine अब यहाँ पर for Bose-Einstein case for Bose-Einstein case sine of
Joker mic one.
is equal to plus and for Fermi-Dirac case it can be plus as well as minus है ना for odd and even values of psi जब सिमेट्राइजेशन है ना एक psi plus psi minus एक में आता है माइनस प्लस आएगा फॉर बोस पार्टिकल्स प्लस जाएगा मान उसमें आएगा -1 प्लस ऑड एंड इवन वैल्यूज आएंगे उसमें फॉर Fermi-Dirac statistics so plus and minus so these plus and minus signs they are we have to factor them in our this how we इसको हमने कैसे see so for a particular concrete of space of for example one particle state अगर हम one particle state को these particles of the same kind how this whether we use Bose statistics or Fermi statistics in case यहाँ पर plus one sign आएगा Bose में यहाँ पर क्योंकि anti-symmetrization condition minus both are same minus both you can have values even and odd के लिए for even it will be 1 and for odd it will be -1 so this equation how we can write it here so we are going to see how it is going to just pan out here so So it's going to pan out here, for example, f of n, जो हमारे पास यहाँ पर now using this symmetrization condition, we can have f of n equal to psi sigma r x करेंगे psi sigma 1 आएगा sigma 2 आएगा sigma 3 आएगा इसी तरह sigma n minus 1 आएगा sigma n minus 1 इसी तरह दूसरा आएगा साइड आएगा साइड आएगा सिग्मा n minus 1 और 1 ऐसे साइड आएगा सिग्मा n minus 1 और n minus 1 so on at the end sigma आएगा और 0 and you will see जो हमारे पास ये है delta at the end delta n so for it's for this chronicle delta which will take into considerations both or n minus 1 times and delta sigma n prime for one particle states. अब ये जो first term है for you can take it for bosons but for fermions the sign flip plus signs are the plus signs that can be taken into this 0 1 psi sigma 1 or psi sigma n minus 1 or psi sigma n or and sigma n dagger sigma n minus 1 sigma dagger sigma 1 or 1 by continuing to move operator psi sigma n r to the right step by step So we can write this equation को हम we can write it in the general form like this. F of n is, so you can now have successively you can write it n2 minus n1, n3 minus n2, n4 minus n3, so on and so forth. इसकी जो permutations continuous. So we'll take sine of Sn. Sine यहाँ पर मिलेगा. So we are going to relate this equation, this equation. This equation को यहाँ पर in terms of Pn लिखा था. So we are going to write it here, but including all successive terms, we are going to write Pn minus 1 or minus 1 delta r n minus 1 or n minus 1 delta r n minus 1. So इसी तरह when we combine the plus ones, we can have sine of Pn minus 1 delta r n minus r prime, so or n2 minus or n minus 2 prime, so on. So you can do the same thing here. You see the third term plus I, first term ultimate term, the first term will plus, the second will have this anti-symmetrization condition, plus minus. The third will plus, the fourth will be again anti-symmetrization condition, the plus minus form. And conical deltas can spin values have been surfaced. So that's. अब इस चीज को हम कैसे in some generalized sense, how can I write generalized orthonormality conditions? How can I write generalized orthonormality condition को हम कैसे लिखेंगे? Generalized orthonormality. How can I write generalized orthonormality relation? If you assume, so if you assume general and particle states, which can be represented as sigma 1, sigma 2. So we can represent it like general and particle states as psi dash sigma or psi dash sigma or so psi dash sigma 1. So we can start psi n minus 1 and minus 2 and then it will be psi n directly, it will be psi dash sigma 1 or 0 f of sigma 1, f of sigma 2, f of sigma or. So if we have integration with the expression substitution and the integration is carried out using this 21.59. So we have, once we started integration, उसका proof हम लेंगे. So psi n को हम कैसे represent करेंगे? Psi of sigma 1 r1 sigma 1 r2 sigma 2 rn sigma n. For n, for permutations we can have n by n factorial sigma 2n. Sign of Pn हमारे पास है. Pn means this sign. F1 sigma 1 f of sigma 1 r sigma 2 r sigma n. And owing to the commutation relations of operators for creation operators, psi n can be represented as psi dagger sigma dagger psi n minus 1 n minus 2 and at the end psi multiplied by this factor 1 by n factorial sigma p n sine of sine p n r1 sigma 1 r2 sigma so on and so forth. अब ये कोई भी वेव फंक्शन साई जो हमारे पास है एनी वेव फंक्शन साई can be related by this we have incorporated this delta function and symmetrization condition for a non-particle state, so we can represent this size as a configuration for SA representation. These are sites, and this is the what I should say. Permitted, this is these which we got is delta functions, and these are side diagrams. ठीक है. अब इसमें हम क्या करेंगे ना? What we should do is we are going to take inner product for this side का हम एक inner product लेंगे and try to see how this inner product will span out inner product of side with side will how it will come uh, uh, how side inner product side of it will side side so it will come out to be sigma. So it will be side dagger. So side dagger. So it will be inner product. It will be side of R1 sigma 1 R2 sigma 2 so Rn sigma n. So side dagger it will be this R1 sigma 1 R2 sigma 2. So inner product it will be square of this. Square of this. And D31 the configuration space is 2 so on D3. So this can be probability of particle 1 with spin sigma 1. Particle 2 with spin sigma 2. Particle 1 with sigma 1. Particle 2 with sigma 2. So on and so forth in this configuration space. So we have done so particle 1 with sigma 1, particle 1 with sigma 2, so on and so forth. You can see that. And can say it, for example, so it's at position R1, it's at position R2, it can be at position R3, so on and so forth. You can say it that. So psi can be R1 sigma 1, R2 sigma 2, Rn sigma n, and जो इसका ये है step, the probability density. For special case of n is equal to 2, we can encounter, for example, helium atom. Helium atom की जैसे 2 electrons अब ये है कि so we can also have the expectation values of how we can write it in terms of matrices of diagonal elements of operators. How can I express the same in terms of elimination and creation operators in terms of wave functions in the multi-dimensional space? So that's the point. It's the n-dimensional space in the any space, 2, 3, 4, 5, 6. So these So how can have expectation values of and all diagonal matrix elements, which was in yesterday's class we saw that for one particle configuration या for a two particle configuration हमने क्या कहा था? Just said that so they can be defined in terms of matrix elements in that sense. तो अगर हमारे पास आप ये है कि फॉर एग्जांपल इफ वी हैव फॉर एग्जांपल इफ P or P if K or P is one particle operator which has a coordinate or and conjugate momentum P. So we have to find the expectation value of sum of operators operator की normalized over n particle states तो क्या है so we can see it in that sense so इसका psi ऐसे है state this is operator and this is psi of n so psi of n can be psi of n can be as sigma integral of psi of sigma delta r prime k of r prime. So you have how we write position operator and momentum operator. You can write it like this. Psi sigma r prime is three-dimensional space. Either as you can see it like that. So at the end, so for j is equal to for j is equal to 1 into n and sigma 1, sigma 2, so on and so forth. This momentum operator and position operator जो है पहले साई स्टार ने इसका एक्सपेक्टेशन वैल्यू कैसे निकालना हमारे पास है एक्सपेक्टेशन वैल्यू साई दैट क्वांटिटी एंड साई स्टार उसका इंटीग्रल so but here we have taken position and momentum this thing operators you can see that psi star r1 sigma 1 r2 sigma 2 so on and so forth k times r prime h by psi 1 r1 sigma 1 r2 sigma 2 so on and so forth r and sigma n ये हमारे पास आएगा for d1 d3 r2 so on and so forth. Now we are coming to what we have done in the yesterday's class. Yesterday's class हमने क्या कहा था? We had discrete eigenvalues as well as continuous eigenvalues. तो इसकी अब representation कैसे हम लिखेंगे? So we at the end arrived at different spin states R2, R3, Rn. So in that in different configuration space, maybe three-dimensional or multi-dimensional. तो उसको हम इसका एक्सपेक्टेशन वैल्यू कैसे लिखेंगे ये तो साइड यहाँ पर है एक दिस इज द operator can be position or momentum operator so how we can write it so we can write this in terms of what I should say so two particles interaction of let's say how we can write the two particle interaction two particle interaction can be as so So the two particle can be written as R prime sigma prime or double prime sigma double prime. Can be written as E of R double prime delta R prime minus R double prime. Delta R double prime minus delta sigma. So these are vertical deltas. Delta sigma double prime minus sigma. So you can write these configurations, this and this at on minus thing. You can start a presentation in terms of continuous and discrete eigenvalues. You can write it this way. And further, if you want to write for n particle state, for n particle state, psi of n v of psi of n, you can write it like this. I greater than j sigma 1 sigma 2 sigma psi times r1 sigma 1 r and sigma f b r I r r. So this is so I'll summarize what we have done. We have done nothing. We have tried to show जो Bose Einstein and Fermi-Dirac statistics की जो how can have representation of discrete and continuous eigenvalue की representation vis-a-vis the commutation and anti-commutation relations. How the operators, how we can the commutation, how the configuration turns out to be. For both statistics, it will be +1. For fermions, it will be minus and plus for odd and even values. And trying to see how we can write them in that configuration space. So that configuration space may be three-dimensional or it may be a multi-dimensional space. But the sides are basically a part of that Fock space. And at the end, and we could see जो उसमें हमारे पास relationship है using delta functions, how continuous eigenvalues are the values they take. So at the end, and even if part of the configuration we can represent them, these states in terms of size, in terms of spin states, sigma 1 and sigma 2. Or sigma 3, sigma n. For two spin states, expectation value in terms of position and momentum operator, you can write it like this. Now there's an exercise here which we have not done. You can see how we can arrive at from this to this. So from this to 6 to 2 1. How can arrive from this to this? So this is an exercise you are supposed to do here. So should we stop? So we'll stop here.